for joining us today. So we will talk a little bit more about Professor Richard Elliott. I know that everyone that has been on our online seminar already know him because he is an important participant in our discussion and have making the discussion even better. So thank you, Professor, for that. And he was also with us twice during this time on an online seminar and in a class for the grad students. So those videos that he gave a lecture to us are already on our YouTube channel. So if anyone wants to see that, so watch that, can go there. Professor Richard Elliott is today an emeritus professor at the University of Akron in Ohio, USA, and teach several chemical engineering courses, many of them in thermodynamics. So he got his PhD in 1985 at Penn State University, and he is the co-author of two well-known books, The Introductory Chemical Engineer Thermodynamics and The Properties of Gas and Liquids. For the ones that I have to thank you, Professor, because those books are really important for us, have been really helpful in our studies and research, important for us. Thank you for that. And with all his experience, he has several research interests, and the one that he will present to us today is the inference of intermolecular interaction potential. So thank you again, Professor, for being with us here and make this seminar for us. So our ears are all yours now. Thank you.
Okay, thank you. Very kind words. Let's see, how do I share my screen again? Oh, I always forget that part. There it is. And this one. Can you see that?
Yeah.
Yes. Yes.
All right, so let's see. Last time I only had about 16 slides, and it took me, I think we ended up talking for 2 hours. So this time I've got 36 slides, and so who knows? But I'm really aiming for 40 minutes. That's what we'll do, and then so I've got to discipline myself to speak a little bit quickly. But on the other hand, I did want to kind of keep it not too heavy, you know, a little bit informal. But still get across some big ideas that, and we can tell some stories, tell some jokes, sing some songs, you know, some little things that maybe make the pandemic a little less oppressive. So that's sort of the idea. I'm trying to keep it a little bit light here, and so I reappropriated a poem that was you might recognize from the Lord of the Rings, and adapted it to this presentation. So when I was in graduate school, I used to talk about the equation of state. And we would be walking to lunch or something with all the other kids in the group, and I would say, well, the equation of state is this way. It should be like that. And then they would ask me, which equation of state are you talking about? You're saying the equation of state. And I didn't have a great answer at that time, but now I'm kind of coming back to it and saying, well, maybe that's not so crazy. There's one equation of state out there that controls, in my slightly crazy perspective, that really dictates all the properties of all the fluids. And it's really what it is it's the force field between all the atoms, and different atoms on different molecules that sort of have the same character, but they evolve a little bit when you put them in different environments. So we don't really know everything we'd like to know about that force field, but it's out there. it's the force field. It's the force field that's driving all the equations of state of everything. And so that's sort of what I've got in mind as the equation of state. It's the force field equation of state, if there's one equation of state. And what we need to do is infer what are all the molecular interactions. And so one of the things that we learn, going back to Laplace, is that it's easier to think about the interactions between particles in terms of their potential of interaction instead of just the forces between them. And so the more general term that I'll use here is interaction potential. But force field and interaction potential, they're somewhat interchangeable, really. And so if we're in search of that force field that drives everything, we need to have some criteria for identifying, well, what are the parameters of it? What are the best parameters that represent the force field? And how do we even write the force field in a way that we don't prejudge what it should look like? One of the themes I'm going to kind of reiterate here maybe more than once is the most dangerous assumptions can be the ones you don't know you're making. And so I want to make sure that we just kind of keep our minds open and maybe say some things that are a little crazy sometimes, but that's okay. As long as we're doing it in a scientific way. We're gonna state, here are the hypotheses, here are the objectives, and here is the mathematical operation of that, and here is the conclusion of that. And so to me, that some things may sound crazy, but as long as you're following that process, you're okay. And so we need to figure out what kind of objective function we need to decide which force field is better than another one. And then we'll have this one force field that tells us how all of the molecules are held together. So that's sort of a story, a background, and then I want to pick up a little bit from where we left off in the last talk about the artifact-free equation of state. And in there we introduced a few things, and one of the things that came up was this thermodynamic perturbation theory. Where do those terms, the A1 and the A2, where do they come from? And we had some questions, and I want to make sure everybody understood that really, really well, because that's the basis for a whole lot of things, not just the perturbation theory in this lecture, but in Wertheim's theory and perturbative virial coefficients that I'd like to talk about someday. But I think you'll notice here I changed the outline a little bit. We're not going to talk about everything that I would like to talk about today. So I'm going to focus just today on just the force field concepts and this inference of the force field. The definition of optimal can be a function of time. And so that's what I'm trying to represent here. And so when we started on this project with this step potentials for equilibria and dynamics equation of state, that's what SPEAD stands for, that was the year 2000. So the constraints in terms of computer power were very different then. And so what was best as an approach for how to model the force field in that time frame was very different than what we might do today. Well, when you're going to choose an optimizer, if you're looking for the global optimum, then maybe you're going to run into local optima that are going to mess you up. And so we should consider stochastic optimizers that just search randomly everywhere, or pretty much randomly, that tend not to get stuck in local optimum, versus a deterministic optimizer. So we'll talk about that briefly. Then this is a concept in general about force fields that essentially what we're doing is we're doing a stepwise forward regression. And that's a well-known methodology within the statistics world. So you start with a kind of minimalistic model, and then you add some new features, some new parameters. And then before you decide to keep those new parameters, you ought to test whether objectively you have improved your model in a meaningful way. And it's easy to get confused about that. The standard statistical test for doing that is called an F-test, and that's got a problem that I'll talk to you about. Then I'll just outline, okay, that's all things that we were able to do with this SPEED approach. What's going on with the next generation? So can we get away from step potentials and start working on more, well, let's call them smooth potentials. I almost said more realistic potentials. That would infer that that they're perfect, okay? And one of the points I want to make is that maybe they're not. And then some methods for doing that kind of inference that would be similar in efficiency to what this SPEED EOS is. So let's start with this brief review then of where we left off. We had talked about second order perturbation theory with the association term from Wertheim. And we said, okay, the A1 term is really simple. It's really just averaging the little u using the radial distribution function from the reference fluid. So for square well spheres, this is just G of the hard sphere equation. And so we know very well how to deal with that. And then this attractive part is just the deep well part of it. And then we said that this A2 term has this n squared minus n squared functionality. I want to clarify why that is. And one of the things we're going to do, instead of just a single square well, we're going to have a series of wells that make the step potential equilibrium dynamics. So that's where all that comes from. We had talked about the shape of this A2 term for square well spheres. And I think I kind of like drew it with my finger as best I could. So I wanted to show you, this is what it really looks like. And over here, we see what it looks like when we're talking about chain molecules. So even small chains like ethane or butane, they still have this single decay, this exponential decay. And that's different from what the square well does. And the reason we talked about was because that square well has that sharp transition from being inside the well to outside the well, and that generates these fluctuations in energy that do strange things at high density where they really shouldn't be doing things according to the perturbation theory perspective. We also talked about renormalization, and I'm not going to talk too much about that in this lecture, but it would come up if I could talk about scaling in the critical region. So I just want to remind you, we did talk about that and sort of keep that in the back of your mind. So now we want to think about other ways of dealing with the force field. So that's our long-term goal. But before we do, I want to explain what we learned from looking at the step potential approach to it, and so that we don't have to reinvent any wheels based on what we learned there. Well, to understand this perturbation theory, I have to say this nasty word, partition function, and generally try to avoid that because I like to appeal to as broad an audience as possible. But when you ever study a statistical thermo course, and I think everybody should, one of the first things you'll see is this capital Q, which really just characterizes the distributions of the atoms and their numbers of microstates and that sort of thing. And so if you look at chapter 4, I think it is, in the undergraduate textbook, where we talk about particles in boxes, and then we say how the Einstein solid shows you how particles can be distributed in energy boxes due to quantum effects, then you understand that oh yeah, things are going to be distributed according to their microstates and macrostates, and that's just what this Q function describes. So it's not too much of a leap from what we talked about in like introductory thermo. And then there's this quantity Z, which is just defined in terms of Q. If you think about what that Z is going to be for a single molecule, in other words, an ideal gas, then this is what that quantity is going to be. And we recognize then that the residual Helmholtz energy then just has the ideal gas part subtracted off. So we get rid of all that ugly stuff. And we're just left with this Zn over n factorial. Well, what is Zn? Well, before I multiply and divide by this quantity, it's just this quantity in the numerator. And so it's just basically adding up all of the instances of the realizations of these energetics, okay, according to this Boltzmann weight. Okay, so really all we're doing is we're adding up all the Boltzmann weight factors. And if we want to break that down into a repulsive part and an attractive part, then we can just multiply and divide by the repulsive part. And then remember that the exponential of the sum is the product of the exponentials. So that's just a very basic trick. And then what you see is you've got this exponential of the repulsive part in the numerator with this same thing in the denominator, and you recognize this is a weight factor. So 0.1, 0.3, you know it has to add up to 1. So we're dividing by the amount that the same amount in the denominator, so that the weight factor divided by the denominator, all added up, is just sums to 1. And then that's essentially just the definition of this ensemble average, where we're averaging it with respect to the reference contribution. Then through this definition of A in terms of L in Q, and following the dots along, we recognize that subtracting off this Zn naught, we recognize that's A minus the repulsive part, and that's just equal to A at, which is what we always call this thing. If we take the exponential of this A at, we know it's going to be something like A1 beta plus A2 beta squared. I'm not writing A2 here yet, A1 and A2 here yet, because there's a factor of n, because it's A1 of the equation of state is divided by the number of molecules, and the Boltzmann factor is in the beta here instead of just being temperature by itself. So I'm just trying to sweep that under the rug for the minute. We'll work it out, make the algebra work when we get to the end. So this is just some kind of weighting factor of beta, beta squared, so forth. And then this is expanding this as an exponential. You know, it's just 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So these two things must be equal then. And now I'm going to use the same trick. The sum of the exponentials is the product of the exponentials, and expand that out, and then expand each of these into that exponential that we talked about as a renormalization. Multiply these together, and what you're going to see is that I'm going to have this term, W1 squared times beta squared, and W2 times beta squared. This is beta squared that's left over in the original. So the W1 squared plus the W2 is equal to this UN. Quantity squared, look where the square is. The square is inside the angle bracket here. So now I can rearrange that and see that W2 is just equal to this same thing, this UN squared, got rid of the beta because it canceled. Square is inside the parentheses, inside the angle brackets, minus W1 squared because of this W1 squared here. Well, what is W1 squared? What is W1? It's just this quantity that we figured out from the first term. So when I put that in, I get UN squared minus UN squared. So that's a pretty important term. It looks like, hey, it should be 0. It's the same thing, right? but it matters a lot whether this square is on the inside of the angle brackets or the outside of the angle brackets. And that's what makes it a fluctuation term. And so that's what's driving all of the physics here, making the A2 reach its maximum when at the critical point, near the critical density, when you do it, quote unquote, right, according to me. Okay, and we talked about that before. All right, so now let's sort of we talked right here. Okay, so we talked about why this shoulder is here, and I want to make I'm skipping a slide and trying to make it short here. Basically, what's happening here, this doesn't have any shoulder. And the reason it doesn't have any shoulder is because instead of just going one deep square well, we transition a little step at a time. And by making those little steps at a time, this extra shoulder that's so sensitive to the molecules fluctuating around that barrier where the square well changes, that extra fluctuation term, that just goes away. And we end up with an exponential decay. And what I'll show you is that if we were to use a continuous force field, it will look exactly the same. So we don't need to have a continuous force field in order to get rid of this artifact here. All we need actually is 2 steps. That would be enough. But here I'm going to use, in this particular set of graphs, I'm using 4 steps. It's kind of interesting that something that's so jagged in terms of its steps here gives you a perfectly smooth function when you talk about the Helmholtz energy perturbation contributions. All right, so that means we're free to start thinking in the more general terms about what the force field, what the molecular interactions should look like. And so what this force field says is, I'm going to put atoms at a bond length of 0.154 nanometers. So there's a hole in the force field. Normally, sigma would be the diameter at which you could no longer put 2 things at the same place at the same time. But we're going to create a hole inside of that potential. And then what that's going to enable us to do is overlap those sites. And once they're overlapping, because this is an infinite well, they can never de-overlap. So that's a fused sphere covalent bond in this molecular model. This one, if you do the math on what a 110-degree bond angle is, it comes out to be 0.265 nanometers. And so we have this one to represent the 1,3 bonding distance. So this is a 110-degree bond angle, as you would expect in any kind of hydrocarbon chains. So we've got a complete molecular model then. So this is a force field. And we can apply this force field to everything as one equation of state that binds them all. So let's go through the entire exercise for all the molecules that we've got and just see what's going on. Can we build a methodology that's feasible for characterizing this one equation of state that rules them all? And it's not going to be perfect, and don't take it too seriously, because I don't. But it's going to give us, we're going to learn some things through the process of going through this. Well, to do that, you've got to extend from just the square well to the multiple wells, and it gets a little messy, okay, because we've got multiple wells, and I've got multiple sites on each molecule. I've actually spared you some difficulty here because I've left off a couple of summations, because I could also have summations over the number of molecules, right? So this I think is just for pure fluids. If we had a mixture, there would be some more summations. Okay, so this is the simple form. One of the things that's really interesting about this is that these averages that we're computing are ensemble averages of the n. I guess maybe I skipped over that. so these are fluctuations in U, but because the U for a square well fluid is basically just the number of molecules inside the well times the energy of being in the well. So I can write this average energy just in terms of the number of molecules inside the well. And that extends then, if I go to multiple wells, it just gets a little more complicated. But there's nothing conceptually impressive about this. But what's impressive from an engineering perspective is that I can compute these ends from the reference simulation. So these are hard chains. Like I said, they've got 110-degree bond angle, 0.154 nanometer bond length. If it's aromatic, then I can change that bond length, right? And so everything is according to the way that we know it should be. And then I can do the simulations and compute how many atoms are this distance away from that atom of that flavor, and just compile all of those distributions of atoms around each other. And then I can compute the averages of the n squareds minus the n squareds. Here's the really interesting thing. I don't know if you noticed, these U values are outside of those summations. So I could compile all of these numbers of fluctuations in one place and have my steps, the depths of the steps, in a different place. And and then whenever I want to compute an equation of state, I say, hey, let's try this series of steps. Let's make it a little steeper. Let's make it a little shallower. Let's change the shape of that interaction potential. And I can recompute the entire thermodynamics. Once I've got A2, A1, A0, that's my entire equation of state. I can go and compute the vapor pressure, the liquid density, the Helmholtz energy, the enthalpy, internal energy, any number of things that you want. I've instantly got that. And how long does it take to apply this instance of the force field and recompute the equation of state? It's milliseconds. I can't even measure it. It's like calculating a z factor from the Suave equation of state, okay, or the Ping-Robinson equation of state. How long does that take? It's the same thing. So I can try any kind of force field that I want and recompute the entire equation of state, compare it to the thermodynamic data that I have, the database that I have, and see, is that force field good? If not, hey, I'm going to cost me another millisecond. I'm going to have to try another one. Okay, so every millisecond, I can try different force fields. And that's the beauty of this particular approach, is that the simulation method comes implicit with what's called a surrogate model. So this equation of state then becomes a surrogate for the force field. I don't need to do the full simulation anymore. I can just apply the instance of the force field that I'm trying and recompute all the thermodynamics from this surrogate model. So this is what I like about the speed equation of state, is because the surrogate model and the force field are so intimately related that it's hard to know where does one stop and the other begin. But of course that wouldn't be worth talking about if the theory was not quantitative. So here's where we've done butane. And the lines represent what we compute from using the perturbation theory, and the points represent what we get when we do a simulation of the full potential in all its glory. And what you can see is up to about a 0.31 packing fraction, everything's great. When we get very close to the critical region, things are breaking down a little bit, but that's a story for another day, okay? We have ways of dealing with that, and I can get you to within about 1% of the critical temperature now. But again, I can't talk about that today because yeah, it's already been 30. Well, wait a minute, I didn't start until 11:08. So now I want you to, before I show you too many results, I want you to just sort of open your mind and think about different ways of describing the interactions between molecules And so one of those ways that I'm hoping will open your mind and maybe lighten the mood here in a pandemic is think about the thermodynamics of hot dogs and hamburgers. All right, and hot dogs, then we can call those as prolate spherocylinders. What's a prolate spherocylinder? Imagine a line segment, just a single infinitely small line. Now wrap the Lennard-Jones potential around that line. Everywhere you are on that line, wrap the interaction potential around it. Then compute the minimal distance from one molecule to the other and just apply the Lennard-Jones potential along that radius. That's called the Kihara potential. And you can see how a prolate molecule like that is going to look like a hot dog. Well, if you do the same thing, but with a disk, so imagine an infinitely thin disk, and now you wrap the Lennard-Jones potential around that, then you'll get a hamburger. Now we can develop the whole thermodynamics of hot dogs and hamburgers. And one of the things you can do is calculate the acentric factor. That's well defined. It's just the negative log of the vapor pressure at a reduced temperature of 0.7 divided by the critical pressure. We can calculate all of those things. And so we'll get the acentric factor as a function of the length to breadth ratio. And now we can get the entire equation of state and compute the phase diagram then for methane plus benzene, where benzene is modeled as a hamburger. So that might sound like a crazy kind of force field, but it's different. This way of interacting, people are having all sorts of trouble describing perfluorocarbons because the individual fluorines are big enough that they ought to be represented by individual interaction sites. But when you represent them that way, it just doesn't fit. Nothing seems to work. Now, you can do a reasonable job by using like CF3 as one big interaction site by itself, but that seems a little artificial to me. So there are reasons why that might be happening, and that's one of the things I want to explain, because this is a place where you might be making assumptions that you don't know you're making. So if we think about the way just a square well sphere wrapped around two interaction sites, how is that interaction potential actually behaving? Well, if you have a probe molecule then that's coming along and it encounters this first square well around this ethane, then it gets attracted, right? It gets deflected, gets pulled in. And then it's going to hit this other interaction site due to the bound atom, and it's going to get pulled in again. So the energy inside of this gray region here is double what the energy is outside the square well. So now this thing that we thought was a square well potential is actually a two-step potential. We have this depth of energy, and we have this depth of energy, and then we have the nothing. Well, if we have isobutane, we can have a three-step potential. In fact, even N-butane has triple overlaps. And so I call this region of double overlap of the interaction sites, that's a kind of a cooperative attraction region. You may hear me talk about that sometime in the future. So this is what I'm talking about. Well, do molecules really act like that? We're assuming that they do. And I think they do a little bit, but it's not as much as we assume they do. So then that raises the question, what should they look like? What should those interaction potentials look like? And what you see is that the CH3 interaction is pretty steep. It looks like a Lennard-Jones. It's 90 and then 16 and then 0, okay, in terms of its step depth. But in terms of a CH2 potential, it's pretty flat. And the reason is it doesn't need to be steep, because it's already generating all of these overlaps just due to being a CH2 in the middle of the molecule. So if you are applying steep steps on top of the overlaps that are occurring here, you're kind of double counting how steep the steps are. That's my explanation for why this turns out to be the way it is. This isn't something I told it to do. It's just something that comes out of analyzing the data. And so I'm being completely objective here. And so you can call me crazy, but it's an objective form of crazy. So optimal is a function of time. So you got to remember in Y2K, we were trying to do these things on serial computers for the most part. And so the beauty of this algorithm is that it's just the hard sphere algorithm. If the molecules are, if the interaction sites are bound to make a covalent bond, then they just go back and forth inside of that well that I said that they couldn't leave. But it's still just the hard spheres bouncing around. And so this algorithm is something that I just copied this out of my introductory physics book. I don't know if you took it in high school or freshman year or sophomore year, but if you go open that book, you will find this picture in your introductory physics book. It's very basic physics. And the beauty of it is, you may have heard of this RESPA method in LAMMPS, where you're doing multiple time steps so that you can increase the efficiency of the calculations. Well, DMD is the ultimate multiple time step method. Instead of just taking the same time step for each individual molecule, interaction site, we pick the interaction sites that are going to collide next, go directly to there, and then we go away. And so the CPU time changes hugely due to that. And this gives us the ability then to try out the different force field parameters and explore what is the response surface. So here's an example where I'm varying the epsilon of the CH3 versus the epsilon of the CH2. And what you see is if you make one small and the other big, then you can get pretty close to the same optimum. And so as we talk about changing those values, we can travel along this valley here and never actually change the error in our function, not by very much. So this is a very smooth, very flat kind of gradient. If we guess the wrong values of CH2, the wrong values of CH3, wow, the root mean square goes up really fast. But as long as we're traveling along this valley, everything's fine. Well, if we want to then develop the optimal force field, one way to do that, and you can see this in the trap force field, the way they develop that is they develop the CH3 interaction, and then they go develop the CH2 interaction, and then they add one more for like a branched. Well, actually, in trap, they keep the CH3 interaction the same, but they very systematically build up this force field, but they do it one molecule at a time. And in that time frame, you had pretty much to do it that way because especially when you're doing simulations of the force field, the full potential every time you want to try a different epsilon or a different sigma. That's very expensive. But it's not likely that it will give you the really global optimum, because it may be that a CH3 that's attached to a benzene ring is not quite the same as a CH3 that's attached to the end of an aliphatic chain. In fact, if we go back to this picture, the CH3 that's attached to isobutane has a whole lot different of interactions than the CH3 that's attached to the end of N-butane. So why should we think that this CH3 should have the exact same interaction potential as this CH3? They're in very different environments. So in order to sort out what those different parameters really ought to be, what we found would work, and ideally you would have to do everything all at once. But what we found was a reasonable, and that would be way too expensive. So what we found as a reasonable trade-off was we picked 7 site types that could simultaneously describe the paraffinic, olefinic, and aromatic hydrocarbons. And we used 27 different hydrocarbons, and we optimized that all at once. So what do I mean by that? So we impose an instance of what are the step depths for all 7 site types. Then we go and compute all the thermodynamic properties of all these 27 different hydrocarbons, compare all those vapor pressures and liquid densities, pretty much what we're using for our objective function. Compare all of those for all of those molecules and see what the root mean square is. And then we compare that to what's our best root mean squared error, and then we do it again. So you can see how that's going to be very time intensive. It's not a very practical approach if you're not using some kind of surrogate model the way that SPEED and B works. And so to give you some idea, it does take us overnight if we want to optimize the force field for something like 50 interaction sites and 400 molecules. So that does take us overnight because we're trying so many different instances of the different step depths for 50 different types of interaction sites on 400 different molecules that are interacting according to the different alignments of those interaction sites. So it's a complicated problem, but we can solve it overnight. It'll be many years, maybe decades, before we can do that. Well, maybe not. There are some surrogate models coming along with continuous force fields. So, but it will be a while before, not decades, but years, before we get to that same level of optimization for continuous force fields. So this raises the question, well, what if we get stuck in a local optimum? So we tried a stochastic search for that. And just in case we were getting in a local optimum, what we found was the stochastic search ends up converging so slowly that we had to go to 10,000 evaluations. And this was a reduced basis set. But, and even then, we didn't get to the level of reduction in the root mean squared error that we got from just kind of getting in the ballpark and then turning on Levenberg-Marquardt, and boom, we get the answer. So what I concluded from that is that the response surface really is very, very smooth. And the critical element then is to get to that flat part of the valley as quickly as possible. So the random recursive search, the stochastic method, is getting us somewhere in the valley. Then once we're in the valley, turn on the gradient search and just go to the optimum. That's the basic picture that I have in mind here. And to sort of demonstrate that, yes, we are coming to the same optimum no matter what initial point we start with, we just tried a bunch of different random values of epsilons and of CH2 and CH3. We saw that no matter where we start from, we always end up in the same place. And I like this graph because it kind of reminds me of a fireworks display. So if I ever create a artwork for my wall of crazy things I've done with thermodynamics, this would definitely be in that art gallery. Now, this is a critical question. I'm on 11:49 now, feeling the pressure. There's a problem in deciding how many different types of site types we should have. So I talked to you about the CH3. Should it be different whether it's attached to an aromatic molecule or whether it's a branch or whether it's just a straight chain? How do we know that we should distinguish those two things from each other? If we use the typical F-test that they talk about in statistics, then all we're going to do is basically we're subtracting the sum of squared residuals for the reduced model, which is going to be a big number. The reduced model doesn't have as many parameters, and so it's going to have more error, right? We know that. And we're going to subtract off this smaller value, the sum of squared residuals for the full model. And if that difference is large, then we're going to say, oh, then we made a huge difference. We made a big benefit by adding that parameter. Well, statisticians have thought about that in the context of large data sets. You know, as time goes on and big data is more and more of a factor, what we realize is if you've got enough data, this difference is always going to be large because it's like the difference between an extensive variable and an intensive variable. The more data you have, the bigger this difference is going to be because there's always going to be some sort of difference between them. And if you got more data, that difference just gets bigger and bigger because you just got more stuff. It doesn't mean the model's better. It just means you've got more data. And we've got so much data now. We're typically using 1,500 data points just to train parts of the force field. And so this test is not a valid way of looking at whether we should add a new force field parameter. And the statisticians have thought about that, and they've come up with these various criteria. What you're going to see is they all tell you pretty much the same thing. And this one is probably the easiest to understand. What you do is you take your SSR of whatever model you're trying, compare it to the SSR of the full model. Because you're taking a ratio, now you're not talking about a difference. More big data will just give you, in fact, it might even decrease the percentage difference, the relative difference between the two different models. And so that's going to be a more meaningful criterion. It also has some sort of penalties for, as you just throw in additional parameters, you know, you shouldn't just get a better model because you just threw in another random parameter that made the sum of squares go down. You should test in a valid way whether that was a meaningful addition of the number of parameters. And so that's what these criteria are doing. And now we're ready to ask some even crazier questions. What should the force field look like? One candidate would be something like the Lennard-Jones force field. Maybe I could do a simplified version of that I call this linear 2580. So I'm going to declare a step in my like square wells at 1.2, 1.5, 1.8, and 2.0. So these are where my lambdas are for the various steps in the step potential. And I'm just going to draw a straight line between the depths of these wells. And so that's what I call a linear 2580 potential model. And you can see it kind of looks like the Lennard-Jones in this case, but that's because I made epsilon at 2.0, I made that into a small number. Another way that I could do just as easily is if this epsilon was equal to that epsilon, I would have a square well fluid. And all of those different possibilities of putting in different epsilons cost me a millisecond to try. So here's a couple of other ways of doing that. One way, I could just have a square well with some rapid decay. How do I decide what are going to be the depths of the wells here? Well, instead of just drawing a straight line, maybe I should use something like a Yukawa decay. And so that's what this green model looks like. And I'm just putting the Lennard-Jones, the continuous Lennard-Jones potential in the background. You can see what it looks like. When we choose this SYU potential, we have to decide what are we going to use as the width for the square well, and then we're going to go and decay from there. We tinkered around with different values because I didn't want to do too many optimizations all at once. We came up with a number of 1.7 for that. Works pretty well. And so we're just going to use that value of 1.7 for everything. Now we're going to ask the question, well, should the interaction potential look like the Lennard-Jones potential? And let me just say this about the Lennard-Jones. Even though, you know, I've got these different steps, I don't have, however many, 11 different parameters for that. I'm just going to use one parameter for the Lennard-Jones. And I've pre-calculated these step depths in order to characterize the Lennard-Jones fluid, similar to how I've decided, well, 1.7 is going to be the best way of characterizing this step Yukawa fluid. So I've got one parameter for my Lennard-Jones. I'm not going to use 11 parameters for that. That wouldn't be fair. All right. And so I've got one parameter in my Lennard-Jones, but I'll have a different parameter if the epsilon is different for the CH3 attached to an aromatic versus a CH3 at the end of a paraffin chain. So those are different parameters, but it's the same Lennard-Jones shape. So let's see what the results are then. And sure, the root mean square error varies, but it's very hard to distinguish whether that's a significant difference for these different models. You can see this one, well, this one is the best, right? So, but it's got 198 decision variables because we treated the depth of every single well independently in regressing this. And so you can see, yeah, we got the least number, the root mean squared error has to be lower if you throw in more parameters. But is that the best model? When we compare it to all the other models, then what we see is this square Yukawa fluid has the smallest value by a significant margin of all these other values. And look at what the Lennard-Jones is. It is bad. So, and the number of decision variables that was inherent in the Lennard-Jones, like I said, I just had one epsilon. So I had 8 different site types for this optimization. I called it 19 for the step Yukawa because I went ahead and threw in the fact that I had optimized that 1.7 to begin with. It doesn't matter because 19 versus 18, it's 63 versus 22,000. It doesn't matter, okay? When it comes to this Bayesian information criterion, well, maybe the square Yukawa is not that much better than some of the others. And so this linear 2580 is one that I kind of started with. And so it's still kind of near and dear to my heart. And so even though you can say the step Yukawa is better than the linear 2580, it's not that much better. And so I went ahead and made a table then for all the different molecules that we had done this calculation for. And what you see is here are the various differences in the root mean squared error for vapor pressure that we get from the different instances. What you see is that 2580 is a little worse sometimes, a lot worse for the branched alkanes, a little better for the alkenes, a little better for the aromatics. So it's kind of a trade-off, and it's really the branched alkanes then that are somehow killing this linear 2580. So maybe what we have to do is go and refine the description for the branch ones to make them a little bit more like a square and then a drop, the way that the square well Yukawa does. And then that would make sort of a linear square well plus be the best. And we'd only have to make that adjustment for the branched alkanes. Why for the branched alkanes? Because there are so many overlaps there. They already have so many steps just due to the interaction site model. Well, this generates then a whole protocol for how we should go about optimizing force fields. And I'll let you read about that in the journal article. But it's a systematic way. You know how I love systematic things. So a systematic and objective way of deciding what's going to be the best force field. Now we can turn the crank on that and optimize the force field for so many different molecules. And we're up to about 800 now. And what we find out is this particular set was 393 training compounds, but for validation, we can just throw in more molecules and apply the same force field that we already used, right? We already developed on the training set. Okay, so I've got about 400 training compounds, but I've got about 800 molecules total that I've simulated. And when we use this force field transferably, then we get about 10% error in vapor pressure with a bias. That just means that there's not a positive or overly negative deviation. We get about 3% error in liquid density, which is kind of a big number. I'm not as happy with that as I used to be. And I think that has to do with the limitations that you remember. Our potential is hard. And another thing is, I can change the depths of the attractive wells at will and instantly recompute everything. But if I want to change the values of the sigmas, I have to go and resimulate everything. And the sigmas have a big impact on what this density is. And I just don't know if it's worth going and doing all those simulations over again. If a lot of people want to use it, and we can do it. There are more efficient ways to do it now, and we could do it if there was a huge interest in doing it. But I think maybe it's smarter just to use the sigmas that we have, and then just use something like a volume translation in the equation of state to sort of fix what the estimated liquid densities are in a practical sense later. And then if we go to tune the parameters of that equation of state, the way that we would sort of like a PC-SAFT equation of state, then we get results that are basically like the DC-Saft equation of state. Well, there's some other things that we can learn. Oh boy, okay, it's 12 o'clock. Let me just sort of outline some of those things. And what we see is the trends that I showed you the first lecture, how those trends look for in alkanes. And then one of the other things we can look at is how they look for something that's a branched alkane for polyisoprene. Polyisoprene can be 1 million molecular weight. Well, we can't do simulations of 1 million molecular weight molecules, so we've got to infer what that trend is going to be. So what I've done here is I've superposed the lines represent the equivalent alkane for the same number of carbons. And the points then are what the results are for the simulations for polyisoprene. And what you see is the polyisoprene is not as repulsive, so the repulsive pressure is not as high. On the other hand, they're more attractive, so the attractive energy is even deeper. So it suggests that maybe it's not possible to use a tangent sphere chain approach for all of these different types of molecules, because it's less repulsive and more attractive. That's going to like a doubly attractive result. And there's no way to superpose a tangent sphere chain approach onto these kinds of curves. Now we're ready to talk about the next generation of force fields. And we've talked about this picture about, so there's a lot that we have already invested. And so I'll just kind of outline that we're going to need a different baseline equation of state instead of just a kind of a Carnahan-Starling equation for the repulsive part. We've learned a few things over the years, and that is that this fundamental measure theory, if we articulate our reference equation of state in terms of fundamental measure theory, it's going to help us a lot when we go to formulate theories of interfaces. And so as long as we're starting over, let's start over with that. And an element of this fundamental measure theory in the context of Saft gamma, which is something Jackson and co-workers developed, is this shape factor. And by introducing this shape factor then, that's going to be an adjustable parameter, and we'll talk about how it's an adjustable parameter in a minute, but it's going to be a number that I can adjust so that what essentially happens is M becomes the number of sites instead of the number of segments. Okay, so that means we can have overlapping segments and we don't have to deal with the tangent sphere approximation anymore. So that's very straightforward to do within the context of this Saft gamma formalism inherent in the fundamental measure theory. So this is our new basis then for our equation of state. For the attractive terms, we can still use pretty much the same things that we learned before, because guess what? They look the same, and they look the same for the same reasons. That the fluctuations are largest at the critical density. And this is for butane, this is for dodecane. The one thing that's maybe making things a little more complicated is that temperature now plays a role. So I don't have one curve for butane, I have 3 curves for 3 different temperatures. How do we deal with that? That's a little bit complicated. So the equation of state becomes more complicated now, but we can still do it, and we've shown how to do that. And we can turn the crank then. Well, here's the demonstration of quantitative accuracy, very analogous to what I showed you with butane at the beginning. And now we can turn the crank with basically a surrogate model that is this Saft gamma WCA equation of state. And what I've done here to demonstrate that is we did the simulations of just the trap UA potential. And then we changed the parameters of the epsilons and the sigmas to be the epsilon and the sigma of the NERD potential and the OPLS UA potential. And without doing any resimulations, we computed these curves. And what you can see is the curves go through the points. So again, we don't have to recompute, we don't have to resimulate the entire equation of state. We can just recompute it from the surrogate model, this theory. Well, there's other surrogate models. And one is called MBAR, and you heard Ed McGinn talk about that. essentially what MBAR can do is you rerun the simulation with different weighting factors according to a Boltzmann factor with the new potential. I'll try and describe that a little bit more detail in a minute. But essentially what you're doing is this weighting factor, this exponential with the exponential denominator, it's always the same kind of functional form, okay? That weighting factor is going to be 0, essentially. If you try to change sigma by so much that any of the snapshots that you took during your simulation, as a result of that change in sigma, they're overlapping to such a large degree of positive energy that that Boltzmann factor of exponential of positive, of negative of positive energy is going to go to 0, right? And so the weighting factor goes to 0, then that means that that configuration with that sigma is telling you nothing. It's just telling you you can't do that. And so that's not going to be a valid insight into this, how sigma is changing. All you're getting is 0. It's a trivial solution. So what you need to do is vary sigma by enough that you don't go outside of this little band. And so the way to think about this is the number of effective snapshots that are valid within within that instance, right, of that force field. And so you can vary the sigmas just a little bit with a 1-step Bennett acceptance ratio before you go into the dark, okay? You can vary the epsilons pretty much, okay? And then what we're going to do here, what this from 1 to n is, it's the number of instances of the force field. The beauty of the multi-step Bennett acceptance ratio is that we can put together more than one instance of the force field, and this tells us how to interpolate between them. So here I'm demonstrating how much more light you shine on in your search space when you have 2 steps in your Bennett acceptance ratio. And of course, if you string together 5, wow, you're doing great, okay? Now, what we're showing here is how this varies as a function of density and temperature. So this is high temperature, low density, and this is low temperature, high density. And what you can see is that things get a lot more sensitive if you're at low temperature and high density. And so we probably ought to have one more simulation here in order to make sure that we're not making any false conclusions about the thermodynamics in this domain. So that's how MBAR works. You might have read this paper, very good paper by Hemin and Gross, and they're using PC-SAFT as their surrogate model. There's another paper long ago from Escobedo where he used an equation of state with histogram reweighting, and he even used like a bad equation of state and used reweighting of the density of states to sort of, it's a in-between method of this MBAR and the SAFT gamma WCA equation of state. Well, another jazzy thing that people are getting into these days is neural networks. So maybe you could use a neural network to train the neural network using MBAR, but just do it for like several hundred instances of the force field. Train the force field, train the neural network, and then you can recompute the all the thermodynamics of a new force field basically as fast as we were doing with SpeedMD. But don't forget, you had to put in all the investments, 4 minutes at a time, okay, for all those different hundreds of instances, okay? But once they're trained, okay, yeah, you can run that really fast. So that brings me to the end. So it's a little, an hour and 2 minutes since I started. I hope that's not too horrible. And so these are the things that we've talked about. These are the things, some of the things I didn't get to talk about today. And so anything you want to talk about, and there's more things that I could list, I left interfaces off of the list here. I'd love to talk about that, for instance. So anything that you think, oh, and properties of gases and liquids. I think somebody wanted to talk about that. So anything you want to talk about, I'm open for. I just couldn't talk about all of it today. So thank you.
Thank you, Richard. It's a lot of information already. It's open for questions.
Hi, Fred. May I start?
Sure.
Richard, thank you so much for the beautiful presentation. I have actually a couple of questions, but I'll try to limit myself just to a few ones. But I classify myself as a conventional, let's say, force field developer. So I'm dealing with continuous potentials. One thing that I became very interested is, does this discontinuous potential suggest any kind of better continuum models that we could apply instead of the Lennard-Jones potential?
Well, that is sort of suggesting this square Yukawa approach, or a step Yukawa approach, that maybe what we need, well, it's definitely suggesting that the way that we're modeling branched alkanes needs a little different perspective than the way that we're modeling in alkanes. That especially when we look at the way that the linear 2580 was had the bigger errors for the branched alkanes, this is saying that the number of overlaps that we're getting due to that branching is the interaction site model is artificial in the way that it's representing that. And so if we wanted to do a better job of that, we need something that's a little bit flatter in the short range, like out to about 1.5 sigma or 1.7. And then it drops down and follows the regular exponential decay. So that would suggest a slightly different shape than what the Lennard-Jones or a Me potential or any of those things are. All of these potentials were developed by thinking about spherical molecules. And yes, the best result that we have for methane, which is pretty close to a spherical molecule. Let's see if I can find that picture quickly. There it is. Okay. So CH4, you can see, yes, that looks very much like a Lennard-Jones potential. But when we look at the CH2, it's very flat. And so the data and the step potentials agree. And that the force field for a spherical molecule should look like a Lennard-Jones molecule, look like a Lennard-Jones potential. But what the data are suggesting is that the force field for a CH2, maybe not. And so we need to open our minds to those distinctions. And I don't know exactly how to do that within the context of a continuous force field.
Yeah, because we also have to take into account probably the use of combination rules, the possibility of having combination rules, right? Because we want to keep it as simple as possible, right? We want to have as minimum atom types as possible and use combination rules to derive the mixed potentials. And if you make potentials that are more complex than the Lennard-Jones potential, probably you will not have simple combination rules.
Well, this raises a question that I skipped over. When we've got a pure fluid that's CH3 sites interacting with CH2 sites, in some sense, it's a mixture. And so we have the combining rule for the epsilon of the CH3 with the epsilon of the CH2. And this raises a question about another assumption that you don't know you're assuming. Everybody assumes that the site-site interaction parameter for that Lorentz-Berthelot combining rule ought to be 0. Who says? Why should it be? You're assuming that. You should ask the question, is that the right assumption, or should we objectively test what's the right value for that site-site interaction parameter? And we've done some work on that, and everywhere we've looked, it's not zero.
Okay.
Did you know what I was talking about there? Should I elaborate more?
We actually use a geometric combination rule, but it should be the same. The same should apply, right? You're talking about the same site.
Well, what we can do is when we use a geometric combining rule, we think of epsilon of CH3CH2 of the CH3CH2 interaction. Let's call that the IJ interaction, right?
Okay.
Okay. So we're going to say that the epsilon of IJ is equal to the square root of epsilon I times epsilon J.
Yes.
That's the geometric combining rule, right?
Yes.
But you left something out. You left out the quantity 1 minus Kij site-site. You assume that Kij site-site is 0. I don't want to assume that.
So that would be a more general approach.
Right. Right. And so now you have a problem. You have to test whether assuming it's 0 is valid or not. And I call that a confounded problem because it's a, you have to impose that assumption for your CH3CH2 and then calculate all of your thermodynamics because it's at the fundamental level of your force field. And so it's on the, all your thermodynamics are essentially integrals over that assumed interaction. And so you want to somehow put the quantity that's on the inside of all those integrals on the outside and say, oh, it's equal to this. That's hard to do. That's a very confounded thing.
Yeah, exactly. But what we observe for this is that if you compare atoms of similar size, probably this contribution will be very small, right? Also the errors due to combination rules overall tend to be small for atoms that have the same size. If you go, for example, if you take an example that would be the extreme, like trying to combine a fluorine atom with an iodine atom, right? So probably this is not a bad idea, a good idea to use combination rule.
Well, you can. It's just
you can, but probably
zero.
Yes.
Yeah, exactly. That's a good example. And so, but it. Well, okay, and this might be an artifact of the SPEAD MD model because what I drew for you, it has all the branching and rings and all of that detail in there. It has hydrogen bonding, but it doesn't include anything about polarity. There's nothing explicit about it in there at this moment. I have some ideas now of how we could go and add that if we wanted to. But what we're doing now in its current status is if there's some inherent polarity to that molecule, it just shows up as a deeper well, right? Or yes. And so and that's going to be fine as long as it's kind of interacting with another polar site that's very much like itself. But then if we go to say, well, now we're going to build a molecule that's out of a polar site with a non-polar site, now you've got that fluorine iodine problem again.
Sure, yes. Even if you have explicit partial charges, you can run into problems when you change the environment because it's not polarizable.
Right, right. So yeah, it gets a lot more complicated, very fast when you start putting in point charges and polarizability. And the problem, you know, one of the things I said was the optimum is a function of time. I'm not sure we're in the time frame where we're ready to solve polarizability with point charges in multiple places.
Richard, what I wonder is, well, Thank you, Bruno. Richard, what I wonder is the number of parameters. If you, well, we have 3 parameters for each square well. And so you have several square well for each kind of pair. So the number of parameters it's very high. So maybe they are very correlated. Is it true?
So here's the thing. Well, let's look at this. Well, let me do this first, and then I'll come back to that. Whoa, where am I going? Thought I was going. Okay, right here. So actually, how many parameters are in this linear 2580? Once I've decided that I'm going to make my steps at 2, 5, 8, and 0, and we tried some different ones like 7 and different numbers there. It really, we did 3, 5, 7, 0. It really didn't make much difference, and so we just kind of settled on 2, 5, 8, 0. And remember, this is Y2K. So when we made that, and then we just stuck with it. Okay, but I really don't think it matters too much. So once we define that it's going to be this 2580 is where we're going to put the depths. Well, now you have 4 well depths, according to your count, right? You were saying it could be 11, but if I break it to 4 wells, there's only 4. But I can make it even fewer than that, because if I interpolate linearly for these 2 wells, then the only 2 parameters I have are this one, and then the sigma, right? So I need to know the outer well depth, the inner well depth, and sigma. So I have 3 parameters in order to specify 1 force field, instead of 2, which is what you have sigma and epsilon for the Lennard-Jones force field.
But you define for this example only 1 sigma. But maybe it's kind of Baker-Henderson perturbation theory. You may need more than 1 sigma to define better the repulsive part.
Right, that would be sort of a next generation beyond the speed MD, where we can recognize some softness in the repulsive part of the potential. I haven't done that yet, and I don't know if it's worth doing within the context of a step potential. I'm thinking about it, especially with respect to colloids. It might be worth doing, but within the speed potential, no. There's no soft shoulder. So we only have these 4 potentials, and now I'm going to show you one more thing. So we have 4 potential steps, but we interpolate 2 of them, so that eliminates 2 of the parameters. So now I just have inner well, outer well, and sigma. Those are my 3 parameters. And when I go to look in this table, then if so for linear 2580, I've got essentially double the number of decision variables as I do for the step Yukawa. I don't know why it's double. Oh, okay, because I used the same sigmas for everything, right? And so I didn't count sigma in this decision variable. So this is just looking at the characterization of the attractive potential. And so the 2580 model has 2 inner well and outer well, and the square Yukawa does not. Okay, so
it's Yukawa means it's a hard sphere plus Yukawa. Because we have double Yukawa, maybe it's better than single Yukawa. Okay, well, understood.
Yukawa has a square well plus the Yukawa after that. So this is step Yukawa. First we have a square well, then we have a Yukawa decay after that.
I got it.
So what we find is, we don't have that many parameters, but we do have twice as many with the 2580 as we do with the step Yukawa. And so we're getting some penalty for that in our information criteria.
More questions, please. Luis?
Fred, may I ask another one?
Sure.
Sometimes we have the right results for the wrong reasons. And what I wonder if with this kind of potentials, what happens to molecular conformations? Have you looked, for instance, at trans-Gauss distributions of the of these longer alkane molecules?
Yes, and so I did not anticipate that question. I have a really nice graph of the trans-Gauss ratio, and so you have to think about what the definition of the potential function is in order to easily understand it. Essentially, there's no reward or penalty for being in the Gauss position according to this this model. So essentially, what the molecules can do is rotate about their dihedral angle until they get into the cis configuration, right? Or try to, and that's not allowed. So in the cis conformation, they're blocked because of the way that a 110-degree bond angle works and the way that the repulsive diameter works. You just can't go into that cis conformation. But it's pretty flat from gauche to trans in terms of the frequency distribution. So what that means is we've got some molecules that are probably not as rigid as they should be. And yet, if you compare some of the results that we got to things that you get from SAFT, which is a tangent sphere perspective on what the conformations are, we're way more rigid than they are. And so you can see that in figures like, especially like this one, okay? So if you were to put tangent spheres on here, I think they're even lower in terms of repulsion than the polyisoprene. And so we've sort of generated some maps of how to go from number of carbons to sort of the equivalent tangent spheres. And that number is actually 7. So what we're saying is you need 7 segments before you become as flexible as a tangent sphere chain. So it's something called a Kuhn segment. And so most people are using 3 for that number because they're thinking in terms not of the conformation, but of the just the repulsive size of the segment. And then you get in, once you start thinking about, well, what is the Kuhn segment definition? And it gets a little fuzzy after that. So yes, we have a definite conformational distribution here. It's definitely not recognizing the distinction between trans and gauche as it should, but it's still way, way ahead of something like a tangent sphere approximation.
Okay, thank you. Yeah, interesting.
The last question, please. I think we are in time to finish, but I open for the last question.
I actually have a couple of questions, but I'll skip all of them, and I'll ask just a quick one. Thank you, Professor Elliott, for your talking. Is this DMD algorithm available?
Yes.
Oh,
so
that reference you mentioned?
Yeah. One version of it is actually in Allen and Tildesley. That's where we started. So yeah, so it's just a really simple thing. I think you can download the algorithms of Allen and Tildesley from their website, from their book's website.
Oh, great.
A fine place to start. And what you'll see is the equations look exactly like the equations that I showed you.
Awesome. Well, I'll skip the other questions we can talk about later.
Okay. Sure.
Just another quick question. Is the database of properties also available? One of the hundreds of that used to parameterize the model.
Yes. So that reference that I showed for JChemie data, That's where we published pretty much the whole database. And if anybody doesn't want to do the simulations, but they just want to take these distributions of n's, you know, these well averages and everything, I've got that complete database too. And so it's kind of interesting to explore, you know, different ideas about what are the trends. I showed you, you know, a few trends like this one, but maybe there's a lot of different things that people could think of extracting. What's the trend? What's the effect of branching when you look at it from a trend basis? All of that data is basically in the that database that we posted with JChemIng data. One thing I'll say, this goes back to the properties of gases and liquids effort. So we're testing SPEED-MD as a model for that. And I've found a number of bugs and typos and things like that I guess you shouldn't be surprised to hear about. But yeah, there are a lot of bugs relative to what we published in that, you know, 5 years ago that I've just really discovered in the last year or so. So if you really want to get into that, just let me know and I'll give you the latest and greatest approaches to that.
Thank you
Nice.
so much.
Ingrid and Thiago and Yuri, I think it's time we finish the
Okay,
the
we
seminar.
can talk about the other questions later. Ingrid and Yuri, please. Could you share the screen? I think Professor
Oh,
Ed,
I have to unshare, right?
yes, please.
Stop share. Okay, got it.
Yuri?
Okay. Thank you again, Professor Richard.
You're welcome. Thank you.
Was a very nice seminar. Thank you for your time and disponibility.